Welcome to Mrs. Lee's Chemistry Academy. Today we are going to focus on reaction mechanism. Tying to the learning objective from College Board 4.7, students able to evaluate alternative explanations expressed by reaction mechanisms to determine which are consistent with data regarding the overall rate of a reaction and data that can be used to infer the presence of a reaction intermediate. 4.8, the student can translate among reaction energy profile representations, particulate representation, and symbolic representation, that means chemical equations, of a chemical reaction occurring in the presence and absence of a catalyst. 4.9, the student able to explain changes in reaction rates arising from the use of acid-base catalyst, surface catalyst, or enzyme catalyst, including selecting appropriate mechanisms with or without the catalyst present. Reaction mechanism. It is a series of elementary steps, and the steps will sum up to an overall reaction. The coefficient in an overall equation indicating the reaction stoichiometry, but not the order with regard to a specific reactant. And out of these elementary steps, the slowest one is the rate determining step that determines the rate of the overall reaction. And the reaction intermediate is formed in one step and consumed in the next step. Reaction mechanism is proposed to fit the rate law determined experimentally. Now remember, reaction mechanism is not what we actually can prove. It is just a proposed model to account for the rate law that's determined from lab data. Here is an energy diagram showing two-step mechanism. Okay, so you have energy versus reaction progress, and we have two peaks going from reactant down to products. The first peak is having larger activation energy than the second one, and at the top of the two peaks we call that the transition state, and it goes through the overall in two steps resulting in the product. Step 1 has higher activation energy EA1 than EA2 in step number 2. Step 1 has a smaller rate constant, meaning step 1 will take longer time to complete, and it is the rate determining step. Let's show a mechanism with initially a slow step, such as the decomposition of nitrous oxide into N2 and forming a radical O that's being slow. Then the next step will be another molecule of N2O combining with this O radical to make N2 and oxygen. Now this step is fast. Overall, when we add up the two elementary steps, we get an overall equation of 2 moles of N2O to make 2 moles of N2 and 1 mole of O2. Now, the O is cancelled because it's an intermediate that's made in step number 1, but consumed in step number 2. The rate law can be written based on elementary step number 1 because it's the rate determining step. So we're going to choose the slow step and then write the rate law based on that, because that determines really the overall rate. So rate is equal to rate constant times concentration of N2O. It is first order in N2O. Now there's another mechanism here with the first step being fast. In 2 moles of NO colliding with Br2 forming 2 moles of NOBr. So initially the first step is fast, NO colliding with 1 molecule of Br2 forming the intermediate NOBr2. It is so fast that equilibrium is reached and is represented by a double arrow. In step number 2, the intermediate NOBr2 colliding with yet another molecule of NO to make 2 moles of NOBr. This is a slow rate determining step. Now based on the rate determining step number 2, we can write the rate law equal to K, the rate constant, times NOBr2 times that of the NO, each one raised to the first order. However, NOBr2 is an intermediate. We cannot see it, we cannot measure it, therefore we must express the concentration in terms of something real, measurable. And so we go back to step number 1. where the forward rate is equal to the reverse rate. That means if we write the rate law, the rate constant forward times NO and BR2 is equal to the rate reverse constant times NO BR2. Now we can rearrange the terms so that the NO BR2 is expressed into real measurable concentration of NO and BR2 with some rate constant. Now we substitute that into the overall rate law, and we can see that the rate is equal to K times the intermediate times NO. The intermediate is in red. Now we are replacing the intermediate with real measurable terms and combining all the rate constant, all the K's together, and calling it a K prime. And so rate is K prime times NO raised to the power 2 times BR2. The intermediate, NO BR2, in the rate law from step 2 is replaced by NO and BR2 from step number 1. The rate is second order in NO and first order in BR2. Practice problem number 1. Given the following three-step mechanism for a reaction, the first step is Cl2 molecule breaks the bond to make two Cl atoms fast. Then the Cl atom will collide with chloroform to make hydrogen chloride and CCl3 that's slow. And the Cl atom will collide with the CCl3, making carbon tetrachloride that's fast. Now what is the overall reaction? Identify the intermediate in the mechanism. And what's the predicted rate law? Practice problem 1, recap. Overall, we have chlorine and chloroform to form hydrogen chloride and carbon tetrachloride. The intermediates are chlorine and CCl3 as they are made in one step and consumed in the next. Predicted rate law is equal to rate constant times Cl2 raised to the power 1/2 times the concentration of chloroform. Now, how do we get there? The slow step is the rate determining step, which is step number 2. So when we write the rate law based on that, we have rate is equal to rate constant times Cl atom concentration times chloroform. But Cl is an intermediate and must be replaced by a real reactant concentration. So we now go back to step number 1. As 2 moles of chlorine appear, 1 mole of chlorine molecule disappears. Therefore, now we can replace this rate of disappearance of Cl2 being half the rate of appearance of Cl. Cl can be replaced by Cl2 raised to the power 1/2. I hope you understand that last sentence. Practice problem number 2. For the reaction, hydrogen chloride and ethene to make ethyl chloride. Here's a diagram with two-step mechanism. Again, the first activation energy is quite large. Suggested mechanism is 1. The hydrogen chloride reacting with ethene to make the intermediate C2H5 plus and Cl minus. And then these two intermediates will collide to form the ethyl chloride. Which one is the rate determining step? Now you can see the step number 1 has to be because there's a large activation energy. Identify the intermediate. Surely it's C2H5 plus and Cl minus because they are made in step number 1 and consumed in step number 2. Write the predicted rate law. So when you write it, it's based on step number 1, and overall reaction is endo or exothermic. Since we get product at a lower energy than the reactant, we conclude it is exothermic. So here's a recap of what I just said earlier. And again, the order is first order in ethene and first order in hydrogen chloride. Overall order is second order. And that the reaction is exothermic. Catalyst. It can increase the rate of a reaction but not consumed by the reaction because it stabilizes the transition state and lowers the activation energy. And it also participates in the formation of an intermediate to provide an alternative reaction pathway or mechanism. There are two kinds of catalysts, homogeneous and heterogeneous. Homogeneous catalysts, such as in ozone destruction, the catalyst exists in the same phase as the reactants. And in heterogeneous catalyst, such as in catalytic converter, the catalyst exists in different phase than the reactants. Now the following diagram will show us a clearer picture. Looking to the left, the yellow round balls represent that of the catalyst, and the pink and green ones represent product and reactant. So you can see the catalyst is in the same phase with the product and reactant in the gaseous phase flowing around in the air. Now with the diagram to the right, the catalyst now is a solid sitting at the bottom of the container, whereas the reactant and the product are gases in the air, so this is a heterogeneous catalyst. Let's look at destruction of ozone, which is classified as homogeneous catalysis. In the upper atmosphere, ozone can be destroyed by ozone and reacting with oxygen atom to form 2 moles of oxygen. Now this is very slow because it requires high activation energy. Look at this diagram. However, with the hairspray that we're using, it can release this chlorofluorocarbon, CFC, into the air, into the upper atmosphere, and similarly with the refrigerant. Now, they can be dissociated by energy from the photon to produce catalyst Cl that would destroy ozone in the following manner. The Cl, reacts with the ozone to form ClO and oxygen. And then the ClO reacting with the O to form chlorine and O2. Now the Cl is regenerated, so the Cl is the catalyst. Overall is ozone and O to form 2 moles of O2. The Cl catalyst, but the ClO is the intermediate. This is the first kind destruction of ozone being homogeneous catalysis. The reaction will go much faster now because the activation energy is lowered and represented by the red line. The second kind is catalytic converter, which is heterogeneous and surface catalysis. Now here's a picture of the catalytic converter. Basically, it's made of solid platinum, rhodium, or palladium dispersed on ceramic surface to convert harmful pollutants such as NO gas and CO gas from the car exhaust into less harmful substances. In this equation representing them being converted into nitrogen and carbon dioxide. It also promotes the complete combustion of any fuel fragment, let's say propane, so that the ozone that acts as lung and eye irritant is not formed in lower atmosphere. The third kind is called heterogeneous catalysis, represented by hydrogenation of alkene. Alkene reacted with hydrogen can form saturated alkane propane. Process is very slow at room temperature. Now, we finally divided platinum, palladium, or nickel catalyst. Hydrogen bond can be weakened by absorption on metal surface, meaning the hydrogen is absorbed onto the metal surface of the catalyst. 2, diffusion. Now this hydrogen atom can then be diffused on the surface to approach the ethene, and now there's a reaction between the 2 reactants, and finally when the product ethane is formed, there will be desorption of the product being released into the gas phase. Fourthly, enzymes are biological catalysts. Living organisms operate efficiently in a very narrow temperature range. Enzyme E is a large protein molecule that acts as a homogeneous catalyst to speed up biological reaction by lowering activation energy without heating. The active site of enzyme has properties and right shape to bind the reactant substrate S by hydrogen bonding or dispersion forces. So the enzyme and the substrate to form ES, that is very fast. And then the next one, for the new product to be formed, it will be slow and rate determining. So as illustrated in this picture, in this diagram here, you have the substrate feeding into the enzyme, and the reaction takes place, and then the product is released. Another example of catalyst is acid-base catalyst, which is homogeneous. In that kind of catalysis, a reactant either gains or loses a proton that will change the rate of reaction, such as in the esterification with sulfuric acid. In this equation here, we have acetic acid, which is ethanoic acid, reacting with ethanol in the presence of hydrogen ion to form the ester ethyl acetate and water. And the rate is increased by the addition of the sulfuric acid. The other one will be the decomposition of sugar, sucrose in sulfuric acid, where it is converted into carbon dioxide and water with the help of the catalyst hydrogen ion. Now the hydrogen ion or hydroxide ion is not a reactant in the process, but it is consumed during the reaction and regenerated when the reaction is complete. Practice problem number 3. Explain why precious metal catalysts are more effective when deposited as thin films on alumina Al2O3 or silica SiO2 with high surface area rather than in a powder form. Explanation. A thin film of metal catalyst spread on a stable support provides a greater surface area of contact than the powdered form, and the rate of the catalyzed reaction would therefore greatly increase. Practice problem number 4. What gases are found in the car exhaust with a catalytic converter? What are the advantages and disadvantages for car catalytic converter working at high temperatures? First of all, catalytic converter is a heterogeneous catalyst that would absorb carbon monoxide, hydrocarbon, and these nitrogen oxide gas to convert them into CO2, water, nitrogen, and oxygen in the car exhaust. High temperature will increase the rate of catalytic reaction, but also increase the rate of corrosion of the catalytic converter. So it does have its own disadvantage as well. So to summarize what students have learned today in this lesson, we learned how to evaluate reaction mechanism to be consistent with rate law determined from experimental data. 2, we related energy profile to catalyzed and uncatalyzed pathways, activation energy, intermediates, transition states, enthalpy of reaction, and rate determining step in reaction mechanism. And lastly, we understand the difference between homogeneous and heterogeneous catalysts and how they function to increase the rate of reaction in chemical and biological reactions. From the team of MLCA, we would like to thank you for watching the video, and we certainly hope to see you again next time.